Okay, so bivariate data analysis. In this video, we're going to be looking at numerical data analysis. So numerical data is data that we collect. Generally, if I was trying to collect information and I was asking you questions to collect that information, if your answer was a number answer, then it's numerical. So, for instance, it's things like, how much do you weigh, or what's your height, or that kind of thing. That data is discrete if only whole numbers make sense. So if I was counting the number of people, for instance, it wouldn't make sense to have part of a person. If I'm calculating averages, my average might come up with a part person, but I should then round my answers in that context to make sure I give a whole number answer. Continuous numerical data is generally data that we weigh or measure. So if we were looking at this, discrete data is generally data that we count, and continuous data is usually data that we weigh or measure. So weights, heights, those sorts of things. So data we weigh or measure, generally. Now watch, sometimes you might look at a table of values and they might all be whole numbers, okay? And so people tend to go, oh, that's discrete then, because discrete, generally speaking, we only have whole number answers make sense. So whole number answers. But sometimes I might be weighing something and I might round my numbers to the nearest kilogram or something like that. So just because my number isn't a whole number when I present it doesn't mean that it necessarily is. So be a little bit careful when you're interpreting those questions. Continuous data, it makes sense to have decimals. So in that context, the decimals actually make kind of sense. So if I was weighing something in kilograms and I have decimals, then those decimals actually mean that they're grams. So the main thing is decimal answers make sense. So when you're categorising data, that's going to be what you're going to do. Now for both discrete and continuous data, it doesn't matter which, what we're going to wind up doing is we're going to wind up doing scatter graphs. So a scatter graph basically will look like this here. So we're going to have a series of dots. Each dot in my graph is a particular observation, and I'm collecting two pieces of information for each dot. So I'll be collecting whatever my x variable is and whatever my y is. Typically what we do with these things is we put the explanatory variable, get my highlighter up. We put the explanatory variable on the horizontal axis and the response variable on the vertical axis. So if you're looking at a question, often their first question that they ask you is which is the explanatory variable and which is the response variable. So if it's not obvious and you're looking at it and you're not sure, if you're going to take a guess, then they should have put unless they're trying to trick you, they should have put the explanatory variable on that horizontal axis. So keep an eye out for that. Once you've plotted all your information, you'll have this little scatter graph thing going on. What we typically then do is run a regression and we put a line of best fit through those dots. Now, that line of best fit is not random. We know for sure that that line of best fit is going to pass through the average of each of my variables. So I would calculate the average for each of my variables and plot that point very definitely. The other point that I plot, if I can, would be my y-axis intercept. But sometimes that won't appear on your graph. Sometimes that sort of is outside of the scope of the axes that they've given you. So in that case, you'll pick any other second point, but you very definitely should find two accurate points and then put your line of best fit through it. The calculator, when you run a regression, will put the line through these things automatically for you. And what the calculator's doing is it's trying to minimise the distance between each dot and that line. They're called residuals, and we'll be talking about those a little bit later. But that's how the line gets fitted. Once we run that regression, the calculator will then spit out an equation, and we describe that as a y hat. That shows me that it's an estimate, and basically it's a linear line. So a linear line, of course it is. So it's a linear regression. So we're going to come up with a linear equation, and that will always look like y is equal to ax plus b. And one of the skills you need to get is to learn to interpret the coefficients. So what is A? The A is the gradient. What is it telling me? And what is B? And what is it telling me? So I've rewritten this over here. Y, as we say, is the gradient, and it tells me for every 1 unit change in x, which is my explanatory variable, how much y will go up or down if it's negative each time. And you need to interpret this in the context of the question. So if x was something You know, if it was weights measured in kilos, then for every 1 kilo increase, you know, then A would tell me how many units Y is moving, and that would depend on what I'm measuring on the other axis, and I'd use those units. B is of course the y-axis intercept. So when we say y-axis intercept, it's the point where the graph cuts the axis, and what it tells me is that when x is equal to 0, what my equation will be doing, what my equation will be equal to. So sometimes that makes sense in the context of the thing that you're looking at, sometimes it doesn't, but that's the way that you need to interpret it and have a look at it. So let's move on. To find these equations, we would run a regression, and we use the equation to make predictions. Generally, the whole purpose of looking at time series data, numerical bivariate data, is to make a prediction. And so once we've got the equation, if I want to predict for any particular value of x, I just replace the x in my equation with the value I want to predict for, and I can make an equation, a prediction from that. The other things you need to know are the correlation coefficients. So when we make a prediction, we want to know whether it's useful, and what we need to know is, well, how strong was that relationship to begin with? Was there much of a relationship, and therefore is it worthwhile making predictions? R is my correlation coefficient, or Pearson's correlation coefficient, and it's going to be a number in between 1 and -1. So -1 is the smallest number it can take, and +1 is the highest number it can take. 0 would show me that I've got no relationship, and a 1 or a -1 would show me that I've got a perfect relationship. If they give you a number more than that, then it's a trick, and they're just trying to trick you on that one. So it tells us the strength and the direction of the relationship. As I say, R equals 1 would show that I've got a perfect positive linear relationship, and that would be shown with a perfectly straight line in an upwards direction. So as x gets bigger, y is also getting bigger. R equals -1 means that I've got what we call a reciprocal relationship. So as one thing's going up, the other thing's going down. And it would be described as a perfect negative linear relationship, and it would look like a series of dots in a perfectly straight line going down. So as x gets bigger, y is getting smaller. So you can see here, if x starts here, I've initially got a high y, and as x goes down, so is my y on each occasion. Okay. If we had r equals 0, then that would indicate that I've got no relationship at all. Now that has a few different looks. So sometimes, again, they set out to trick you. If I had a graph where I had a series of dots in a perfectly vertical line, then there's actually no relationship. Even though I've got a perfect line, as x changes, as y changes, x is making no change at all. X is just one fixed number. So there's no relationship between x and y, and that would give me an r value of 0. If I had the same sort of thing but it was a horizontal line, it's the same deal. X is changing, but y never changes. So there is no actual relationship between the x and the y, and so therefore I would have an r equal to 0. And my third possibility for an r equals 0 is that I could have dots all over the place, and I can't even tell if I was going to put a line through that whether it would go up or down, and so in this case r would also be 0. So all three of those graphs would be represented with an r value of 0. We then, if we have an r value that's in between -0.3 or +0.3, we would say that there's no discernible relationship. There's something very mild going on, but we couldn't really use it to do anything useful with. If my r was between 0.3 and 0.5, or between -0.3 to -0.5, I would be saying that I've got a weak positive linear relationship or a weak negative linear relationship. And the features of the graph, often the question will ask you, sometimes they ask you to actually find r, but sometimes they'll say what features of the graph indicate the nature of the relationship. So the features of this graph would be that the dots are very widely spread out around that line of best fit or regression line. That tells me that the relationship is weak. The line as x goes up, y does go up, and so therefore that would tell me that it's positive. And my dots are roughly in a straight line, that tells me that it's linear. Likewise, if it's negative, here I've got a weak negative linear relationship, and we should be using all three words. So 1 is the strength, 1 is the direction, and then we should have a linear or non-linear as our third statement that we make when we describe relationships. If my r was between 0.5 and 0.7, if it was positive, I would say I've got a moderate positive linear relationship, or if R was negative 0.5 to negative 0.7, I would say that I've got a moderate negative linear relationship. And again, the features of the graph, my dots are relatively closely clustered around that line, and it's going up or down, and so on. If I have an R of 0.7 to 0.9 recurring, so anything up to the 1, so it's not quite perfect, then I would be saying I've got a strong positive linear relationship. Or if I have an R of negative 0.7 to negative 0.9 recurring, I would be saying that I've got a strong negative linear relationship. And again, if they ask you to describe it, sometimes they say describe it, so I can use my R and just use the word strong positive linear. If they say what features of the graph tell me that, well, my dots are very, very closely clustered around my line. That tells me it's strong. As X goes up, right, and we should label these, of course. As X goes up, so does Y, so that tells me that it's positive. And it follows a straight line, so that tells me that it's linear. Okay. And of course the ones we've already talked about. Now, if you don't have to in this course actually calculate the correlation coefficients. You would only be able to do those on a class pad and run a regression. However, you should be familiar with the formula. We're not going to dwell on it, but basically it's the covariance is what's on the top here, divided by the standard deviation of each of the variables times by each other. And I've put the formula for the covariance there. It's basically a measure of each score, take away its average, and that should have been a Y. Not bad. And over here it would be Y, take away Y hat. And that would give me my covariance over the number of scores. And the standard deviation we covered last year is each score, take away its mean squared. It's the sum of those scores divided by the number of scores, and then we square root it. You won't need to calculate them, you just need to understand it. So basically, and when I say understand it, the bigger the standard deviations, i.e. the more spread out those dots are, then that would make my denominator here bigger, and if I have a big denominator, I'm going to have a low value coming out of that fraction, and therefore I'd have a low R. And visually you can see that. If my dots are spread out, my standard deviation is going to be higher, and therefore my R becomes lower. Now, and that's called Pearson's correlation coefficient. The other statistic that you need, and that is that one, sorry. So that's the one up the top here. R squared is called the coefficient of determination. So it tells us what, and it's literally just the R value that you've already got from your calculator and you square it. It tells us what percentage of the change in Y is explained by changes in X. We never will use the word scores, never, ever, ever, okay? But we will say it's the percentage of the change in Y that's explained by changes in X. So for example, if I had an R squared of 0.72, that would be telling me that 72% of the changes in Y are explained by changes in X. Now to get this regression equation, so to get your least squares regression line or your regression equation or your line of best fit, they can call it any of those things, and to get R and R squared, what you're going to be doing is running a regression on your stats app. So using your stats app on ClassPad, you would enter your data. We're going to do an example in a minute. And then you'd go to calculate regression, linear regression. It'll come up with a little box asking you for your X list and your Y list. Typically, they'll give you the explanatory variable first. So you put that in list 1, put your response variable in list 2, and you would ask it, again, it's a good habit to go into the copy residual and ask it to pop that into list 3. Because we always need to check the residuals, we'll talk about those in a minute, to make sure that our equation is in fact linear. And if there's a pattern in the residuals, then we're going to say, well, no, it's not linear and we shouldn't be using it. And by pattern in the residuals, we mean chunks of positives or chunks of negatives. It's okay to have a few consecutive positives, a few consecutive negatives. That's not a drama, but you should sort of move between positives and negatives, not just have massive chunks of them. And we'll show you a couple of graphs to explain that a bit more. After using your equation or the trace button in your ClassPad to make a prediction, you must always remember to comment on the reliability of your estimate. And that's going to be based on your R or your R squared, so you're looking to have a high R value or a high R squared value. You must also comment on whether you have got an interpolation or an extrapolation. And finally, you must comment on whether or not you've got a linear equation. And that comes from, is there a pattern in your residuals? Now, interpolation and extrapolation. Let's just explain this for a moment. So, an interpolation is when I'm making a prediction within the range of X values that I have. So if I've got data within these ranges, you can see from my dots, I've got data in this range. Any prediction that I make within this zone would be an interpolation. Now, so for example, and I'll just change colours, if I was wanting to make a prediction at this particular X value here, then I would be coming up to my line. That would be my predicted value, and I would read that answer, of course, from my y-axis on the other side there. If I want to make a prediction outside of this zone, so if I wanted to make a prediction anywhere in this zone, then you can see I've got no data there. So anywhere up there would be what we call an extrapolation. And it doesn't mean we can't use it. You know, if my extrapolation was very close to my data, if I was immediately in that area just beyond what I had, then I would have, if I had a high R value as well, I'd be a little bit confident in that data. But generally speaking, in your exams, if you're in extrapolation territory, you're going to comment that it's an extrapolation very definitely, and you're going to say therefore it's not reliable. And the further away that prediction is from your data, the less reliable it would become. And finally, of course, the last thing you're going to look at is it in fact linear, and that comes from the residuals. So let's talk about residuals. So residuals are the difference between what actually happens and what you predicted would happen. So what we predicted would happen is coming from our equation, and what actually happened will either come from an observation, so what you can see on a graph, or what you can read from a table, or sometimes they'll give you a coordinate. So they'll give you a coordinate pair, just an X, not a mean. So they'll give you an X and a Y value. And in that case, this is what actually happened. I could substitute this X value into my equation. So here I'll be substituting that into my equation here to make my prediction. That would give me my Y hat. And then I'd compare it with what actually happened, which is what they've told me here. So what actually happened, as I say, you're going to find what you predicted, you're going to have to put into your equation. So if they've given you a coordinate, you're going to substitute in, and away you go. Visually, what's going on with these residuals, and I'll just change colours over here, is we're finding the difference between what actually happened is what's on there. I just might make this a little bit skinnier, and what we predicted would happen would be on this line at this point. So that difference would be my residual. So again, from each data point, that line up to what would have actually happened. So what actually happened was my dot. What we predicted would happen would be on the line, and this difference here is my residual. Okay, if I try, and you can see here my dots are sort of nicely distributed, positive and negative. So this one up here, I'd have a positive residual. This one down the bottom here, I'm going to have a negative residual. If I actually had a curve, so you can see on the right hand side here, if I had a data that actually made a curve and I tried to put a straight line through it, sometimes I'll actually get a fairly good R value. So if I did a quick little one, if I did a curve like this and then I tried to put a line through it, my dots actually aren't far from my line, so my R value might come out high, but obviously it's not actually a linear equation, so I shouldn't really be using it. I'll just take that off so I don't confuse you later. Okay, so in this case, when I came to do my residuals, what would be happening is I'd have a negative, another negative, and then I've got positive, 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 another positive there, and then I'd have negative, negative, negative. So you can see I'm going to have these chunks of positives and chunks of negatives, and that would tell me that there's a pattern in the residuals, and therefore the equation was never linear, and I shouldn't be using it. When you come to graph these, make note that is the X value that's going on this axis, and it's the residual that's going on this axis. Oh, sorry, no, it's not. Oh, bad, I'm rushing ahead here. That's just my X and Y. Oops, That's just my X and Y, and I've got another one down below where I'm now going to plot it. So what they'll often get you to do is to graph these residuals. And basically what they're doing, if you can visualise, they're taking this graph and then they're flipping it to make that line of best fit horizontal is all they're really doing. So when we come to graph it, and this is what I was talking about there, it's my X that goes on to this horizontal axis, and it's the residual value that's being plotted on the vertical axis sort of along here. So each of these dots would just be lining up with here. So initially I'll change colours. So initially, you know, I've got a positive one here, and that would be my positively one there. Here I had that negative, and that would be my negative one there, and they've just been plotted on. If I plotted the one above, which came from the curved data, you'd see I've got these chunks of negatives, and then I've got chunks of positives, and then these chunks of negatives. So in that case, it wouldn't be appropriate to use that equation. The only other thing they can try and trick you with is at times in your book you'll see that you've got sometimes the residual is measured in the other direction. In that case, what they're doing is they're regressing x on y. So what they've done is changed which variable is my explanatory variable and which variable is my response variable. And so typically they don't really do that, so don't assume that they're setting out to trick you, but just keep an eye on it. If they've done that, if they gave you an R value, typically when we were at R, we'd go R, X, Y, and my first one is my explanatory variable, and my second one is my response variable. So in this case, what they're doing here is they're making my explanatory variable the Y and the response variable the X. So they've switched it. And what that would produce would be X hat is equal to AY plus B. So we've changed what we're predicting from what. The only other thing you need to concern yourself with is outliers. So if you're looking at this graph here, you can see the bulk of my dots are in this zone here, and I should have that purple line going through it. But if I had an outlier sitting on here, what would happen is that my line of best fit would get sort of artificially sort of moved. Sorry, get that moved. My line of best fit would get artificially shifted over here, and it would put out my whole equation. And it would certainly reduce my R value because my dots are going to now be quite far away from my actual dots and where they should be. So if I get this kind of thing, what I should be doing is deleting the outlier when I find it and then rerunning a regression. I would comment on the fact that I've done this, and I would justify doing so by quoting the R value before and after I removed the outlier. And you should see that your R value will increase after you've made that change. Okay, cropping is the only other thing we do. I haven't seen them do this in an exam yet, but they certainly could. So cropping is when I've got sort of a relationship going on, and that's sort of working. And you can see if I was going to put a line of best fit through here, that it would kind of work. And I've got a relatively moderate to strong positive linear relationship going on over this domain between these x values. Okay, but beyond that, on the other side, the relationship breaks down entirely and my dots are all over the place. So I could crop all these data points off, get rid of them, and then really only work in the domain in which the relationship does hold. Okay, let's do an example. So this is your question from the CLUP textbook. It's from the review questions at the back. It's question 8. So it says an ice cream vending van owner keeps records of the profit of sales for each month. Recorded to the nearest 100. Do watch for little tricks when they start doing that, because you need to reinterpret your answers back in that context. And they're plotting that against the average monthly temperature rounded to the nearest degree. Okay, so we've got our table of values. You can also see that what they've done is they've given you some residuals, which is the difference between what actually happened and what they predicted, and they haven't completed that table. So when I run a regression, if I turn the residuals on and ask them to put into list 3, I'll just be able to transfer that data straight into my table. If I don't do that, then I'm going to have to manually calculate them all. So it's a good habit just to put those in. The first question, identify the response and explanatory variables. Well, my temperature is obviously going to be the thing that explains my profit, because I'm going to assume that temperature is going to alter how many people are going to want to buy ice creams, and therefore my profits. My profit could not change the temperature. So my explanatory variable in this case would be my temperature, and my response variable in this case will be my profit. Now plot the data from above. I've already done this just to save time. What you must remember though is the little things. If you're asked to plot this, you must remember there's always marks. You must have a title, you must have a label saying what it is you're measuring and in what units, in this case in degrees Celsius. On my other axis I'm measuring profit, and that's in hundreds of dollars. So what am I measuring? What units am I measuring them in? In this case, they've provided our axis with broken axes already, but if you need to break your axes, then you need to remember to either put that zigzaggy mark in there, or the little slash, which just show that I've broken the axis, and then sort of measure this out. So my lowest score there was nothing lower than 15 and nothing higher than 40, so I've just spread my data out over there and then plotted them, and you're all capable of plotting. Now, what wasn't one of the points was the mean. But what you can see here is that what I've done here is I've put in remember I said that your line of best fit, when we go to fit one, and we will need to, must always pass through the x mean and the y mean. So I've found that, and I've plotted that point in orange here. And you'll see in a minute I've also plotted the other one. So it says plot the above data. That's just my data points plotted. Determine the equation of the least squares regression line that models the relationship. And so to determine the equation, I'll just show you what I've done on the class pad. So I've put my data in, and then I go into calculate, regression, and I would have tapped on linear regression. That's going to bring up this next screen. My data was already in list 1 and list 2. If they tricked me and they put the explanatory variable was actually the other way around, then I can click on these and I can switch that to list 2, list 1. Copy residuals, get into the habit of putting this here. I can already see that I'm going to need residuals, so rather than calculate them, I've asked it to put it into list 3, and that's going to calculate all those for me. That's going to bring you to a screen which is going to give you the equation. It doesn't write it in equation form, but it reminds you up here that you've got the equation, and it gives you the value. So you can see here my A is 1.26, that's going to go into there, and my B is negative 7.27, and that's going to be translated into there. You should also record at this point your R value, you're almost definitely going to need that, and your R squared value, you'll almost always need that as well. So we'll put all those things in. Once you hit on your OK button, it's then going to plot the data for you. So you can see a couple of things have happened here. First, it's calculated my residuals and it's put those into that list 3. It's also plotted all my data points and it's put this regression equation through. So if I wanted to make predictions, I could then put on the trace and predict it straight from that, which is my safest way to go because I'll have no errors. But away we go. So first I'm going to write down my equation. So it said determine the equation. So we just got all those variables from there. So y hat, to show that it's a prediction, was equal to 1.26x, take away 7.27. The number of decimal places you go to is always an issue. In an exam, it's safe to go to about 4 if you don't have a context of the question, but otherwise take it from the context of the question. Here I'm just going to go to 2 decimal places because my profit was in hundreds of dollars, so I'm probably going to times it by 100 at the end, so I'm going to move that decimal 2 spots later on. Alright, so that was my equation. Add the least squares regression line to your graph. So as I say here, that was not a data point, but I know that that line must go through my averages. So I calculate my averages, and just as a reminder, if you needed to do that, you're going to go into calculate. You have to tap on your data at the top because you must be in that section. There you'll get the calculate option, and you want to hit on one variable. It's going to say that your X is in list 1, tap on your OK, and here you can see there's my X mean, 25, so roughly 25. I'd do the same again for my Y, so I'd go back into that one variable, this time change it to list 2. It's going to say X, but of course it's actually my Y data that's in there, so that's going to be, give me a Y of 24. So that's where that has come from. So that gives me my coordinate of 25 for my X, 24 for my Y. I need one other accurate spot. Generally my y-axis intercept would be the one I'd want to do, but in this case my y-axis intercept isn't going to fit on this graph. It's outside of the domain that they've given me. So any other point would do. Pick a point towards the end. So generally speaking, go for your minimum or go for your maximum. If you don't have time to find the averages, do the same. Pick them at either extreme so that you start your graph in the right spot. So here I said, well, I'm going to see it when X is 15. So when X is 15, on my class pad, I could use the trace facility, and that spat out this 11.6. Otherwise, I can replace this X here with the 15 and calculate that from my equation. Once I've got my 2 dots plotted, I can basically then just put a line through. So I'm going through my 2 dots, extend your line right through your graph, and that would be my least squares regression line. Determine the correlation coefficient. We saw that on the screen already. So my correlation coefficient for the data was my R is equal to 0.9525. And that tells me that I've got a strong positive linear relationship. And I've explained that there. complete the fourth row of the table. That was our residual, so we'll go back to there. It didn't ask me for my R squared, but my R squared, I'll put that on the side, was equal to 0.9072. That tells me that 90.7% of my changes in Y were explained by changes in X. So in this case, 90% of my changes in temperature, 90% of my changes in profits are explained by temperature. Okay, I also should have talked about explaining these coefficients here. So this 1.26 means for every 1 unit change in X. So in this case, my X is in degrees Celsius. So for every 1 degree change in temperature, what's happening to my sales is that they're going up by 1.26 units, which in this case is hundreds of dollars. So my sales are going up by $126. If my temperature was 0, so my X was 0, I'd be selling negative 7.27 ice creams. That's what that second coefficient tells me. And obviously that doesn't make sense in the context of this question. I can't sell a negative amount of ice creams. But that's what is going on there. Okay, complete the fourth row of the data. So if you put in your class pad and ask for the residuals, you'll be able to complete the table just by giving the information from that list 3 here. And I'm running out of time, unfortunately. And then we're going to plot it onto this residual plot. And so literally you're going to get each of those residuals and plot them on here. I'm unfortunately out of time, so I'm going to have to put this in a second.